Today, we're going to explore how the heritage-listed Mt Crosby Weir Bridge was transformed from a decommissioned single-lane road bridge into a flood-resilient pedestrian pathway, featuring a new, innovative, collapsible, fibre-reinforced polymer handrail system. Good morning and welcome to our webinar, Transforming Heritage Through Smart Retrofitting. I'm Georgia Lance, Marketing Officer at Wagner CFT, and I'm here with today's guest speakers, GHD Technical Director, Bridges, Matt Williams, and Pensar Project Engineer, Structures, Sam Strofield. Matt is a bridge engineer with over 20 years' experience designing road, rail, and pedestrian bridges across Australia and New Zealand. As a technical director in GHD's Bridges team, Matt is interested in extending the life of existing infrastructure through strengthening and repurposing solutions. Over the past decade, Matt has played key roles in various Mt Crosby Weir Bridge projects. His involvement has included structural assessments of the existing Weir Bridge, concept designs for widening and strengthening, design and construction phase support for the downstream duplication bridge, and most recently, the design of modifications to repurpose the existing bridge as a pedestrian crossing. Sam has over 15 years of experience in the construction industry, beginning his career as an apprentice carpenter and progressing to become a qualified carpenter. Through hands-on experience on site, he developed a strong foundation in workmanship, problem solving, and team collaboration. Eager to broaden his expertise, Sam pursued a university degree in construction management, strengthening his knowledge in project planning, cost control, and contract administration. For the past 5 years, Sam has been working with Pensar, successfully delivering projects ranging in value from $500,000 to $5 million. He has managed diverse scopes of work, coordinating subcontractors, suppliers, and clients to ensure projects are completed safely, on time, and within budget. Sam brings a practical, solutions-focused approach to every project, combining trade experience with strong leadership and communication skills to achieve high-quality outcomes and build lasting professional relationships. We're also joined by Wagner CFT General Manager for Australia and New Zealand, Ryan Leeson, who will be facilitating the Q&A session at the end of the webinar. Welcome, Matt, Sam, and Ryan. Before we get started, just a few webinar protocols. We are recording today's event and we'll make the recording public via the Wagner CFT YouTube channel. You can ask a question anytime during the webinar via the chat bubble at the top of the screen. However, we will hold your questions over to the end of the webinar for the Q&A session. And for anyone having difficulty accessing that chat facility, feel free to send me your questions on the mobile number that I have just popped in the chat now. So let's dive into today's webinar. I will hand over to Matt.
Thanks, Georgia. So I'll just share my screen here. Yeah, thanks for the introduction. Sometimes I always forget about how many different little projects we've been involved on this site here. It's quite a challenging one because there's so much on the ground and so many previous works that need to be coordinated with. So I'm a technical director with GHD in Brisbane in the Bridges group. And yeah, today's presentation, although it's focused on the balustrades for the almost 100-year-old Weir Bridge, to discuss the design for that and how it's actually achieved, we need to go through a fair bit of history of, well, an appreciation of the site, which has a lot more fun to do with history and old photographs and things like that. Before I get started, I'll just sort of show even these two intro images here. On the right-hand side, this shows what the bridge looked like. I think this photo's from about 1940. So for most of the bridge's life, this just had a chain wire fence along the edge. Then it went through a change with traffic barriers on the edge. And on the left-hand side, there is pretty much what it looks like today when Pensar finished the installation of the CFT system. So it's fantastic to see, like, this bridge is 100 years old. It's got it's at the end of its usable life as a road bridge, and the road bridge wasn't even its original use. So it's fantastic to see it getting repurposed and able to be used for pedestrians and cyclists for who knows how much longer. So I'll just, before we get started, there's a little history of, a little location of where the bridge actually is. It's on the pin on the bottom left there. It's actually quite close to Ipswich. It's on the Brisbane River. You can follow it winding all the way from the mouth up to the near Ipswich there, but it's downstream from Wivenhoe and Somerset, so it's still subject to all the same floodwaters. The volume of water comes through there that we've all seen on the news many times, inundating Brisbane. So this is actually the point, it's the furthest upstream tidal zone of the Brisbane River. Not that that's particularly useful, it's just an interesting little tidbit for us. Start our little trip back through time. The first crossing I'm aware of at this site is back in 1884, approximately. I had to do a bit of guesswork with some of the numbers. Would have been built at the same time as the East Bank pumping station you can see in the background of this photo. So that in itself is a fascinating building. I think a few years ago they even opened it up for Brisbane Open House. It's worth it if you're a bit of interested in some of that older infrastructure. But this bridge is an old timber bridge. I think it lasted about 9 years before the first flood came through and completely wiped out this crossing. Which the next few slides I go through, you'll just see a trend. I'm just trying to demonstrate how much water comes through the Brisbane River that any infrastructure built in the river here has to actually deal with. So that bridge was wiped out in the early 1900s. A replacement was built. This is a more robust construction. I think this one holds the title of the only previous bridge that hasn't had significant damage from a floodwater. This one was only replaced when the weir was upgraded upstream of it. The foundations for this bridge, the remnants of that are still visible today underneath the new road bridge duplication that we completed a few years ago. In fact, a lot of that bridge was set out to miss these heritage listed foundations in the base there. So this second bridge lasted up until the weir was upgraded. So this starting to look quite similar to what you'd see on site there today. This is 100 years ago, 1926. In the top left photo there, you can see that second bridge still spanning the river downstream while the new one is being built. The new bridge there, the weir was getting built. The bridge is an integral part of the weir. It lasted approximately 1 year till the first big flood came through. So that photo in the bottom right, I believe, is from 1927, 1 year after the bridge was complete, where the full western approach was washed out. So again, just an opportunity for another fun photo, but it's just trying to demonstrate how much water comes through here. One of the other key things worth pointing out here is you can see our friends standing on the tram tracks that are still spanning where the approach used to be. The fact that this bridge was designed to carry a tram was its primary purpose is actually quite relevant to even the design of the balustrades we put in today. I'll touch on that a little bit later, but just to remember that that's a key thing, that this bridge was originally designed to carry trams backwards and forwards along the weir to aid construction, but also to supply coal to that pump station on the east bank. Okay, so I believe it was only a year later they lengthened the bridge, so built 1926, half wiped out 1927, lengthened in 1928, and that's largely how the structure is still there today, with a few strengthenings and updates along the way. The photo on the right-hand side there is from 1984, shows the bridge lengthened. You can see the original abutment location downstream from it. This is an interesting photo because it's while they were building a new pipeline across the river, fully dewatered the Brisbane River downstream of the weir here to be able to build that pipeline. But it's a unique opportunity to get an appreciation for how much water comes through here. I think you can see one person, like that pipe is almost 2 meters in diameter, to get an idea of the size. You can see the height of those piers, how much water comes over that weir. The length of it's almost 150 meters long, that original, the lengthened bridge, sorry. So just trying to emphasize how much water comes flying down the river here. Left-hand side is just that same photo from 1940. I believe the tram was already out of like disused at this point, but those tram tracks are still embedded in the rail in the deck there today. I like that photo because it shows it spanning a few ranges, got the vehicles driving on the bridge, but also got pedestrians and our cyclist friends using it in 1940s like they will be today. So then we, now we're up to what the bridge looked like quite recently. In about 2000, the chain link fence on the edge was replaced with a folding traffic barrier system. And I'll go through a few points about traffic barrier system shortly. The photo on the right shows it folded down soon after a flood, and I included this photo mainly to show you can see the debris up the banks there. So we saw before how tall this weir is above the actual riverbed. But then when this flood water came through, the debris up the bank there shows just how high that flood water was coming up the bank. So I guess I know I'm harping on this point, but it's not just an academic exercise of what water might come through here. This bridge gets inundated frequently and comes through quite quickly as well. So the next photos is actually one of the few photos I have available of the bridge actually in flood. I don't think this is anywhere near as high as it's been as we saw from those debris photos before. I think this is just probably the highest where someone was going to actually get near the bridge and take a photo, because the floodwater continues to rise quite quickly from this point in one of the flood events. So this was from 2011 flooding, which was quite a considerable event for flooding in Brisbane. And this was the first event where some of the issues with the previous folding balustrade system, traffic barrier system, were identified. So on the left there, in 2011, the balustrades were folded down in preparation for the flood and restrained as they're designed to be. And they had done that before. These traffic rails are in 12-metre long sections. One of them came loose. I'm not sure how, whether it wasn't tied down properly or if the actual tie down was damaged by debris or something during the flood. But anyway, that section came off the bridge and tore the whole. You can see where it was connected at 5 points along the bridge deck there, and it's just taken all that concrete out with it. So I think this was the first event where they appreciated where Seqwater could appreciate how limiting the capacity of that bridge deck was. The photo on the right-hand side here, this is after the 2022 floods. This is just before we started construction of the bridge duplication downstream. In this event, I believe the flood water came up very quickly, and there wasn't actually time to get in there safely and fold them down before the event. So the full folding traffic rail system was actually left up and got the brunt of the full flood water, and it came off like a zipper the whole length of the bridge. I haven't got a close-up photo, but the whole side of the bridge looks like that photo on the left, with all those unreinforced pieces of concrete pulled out with the posts. In fact, the bit hanging off the bridge there, you can see a few bits of concrete hanging on the bottom of the post there. So now these photos from the flood damage, I really want to emphasize how weak the actual edge of the bridge deck is there. I've got a bit more info on that. This is a photo of a snip of original 1926 drawings for the bridge. So it's hard to make out, but the tram tracks in the middle of the bridge there, immediately underneath those tram tracks, there's two considerable beams that are heavily reinforced and provide a lot of support for the tram, which is what the bridge was designed to carry. There's beams on the edge, which are well reinforced as well and provide resistance, but the bridge deck in between these beams is largely nominally reinforced. The bridge was designed to carry the tram traffic. Apart from that, it would be foot traffic or very small vehicles, horse and cart sort of things, probably at the time. So there's mesh in the bottom, a fairly nominal mesh in the bottom. Apart from that, the bridge deck is largely unreinforced. So it's not surprising that under the huge flood forces, I don't think I mentioned, I think at the peak, those flood forces, the flood event can be up to about 5 meters per second coming through here. So fast, a lot of water moving very fast with a lot of debris from upstream. So it's not surprised it'll just tear the concrete off an unreinforced piece of concrete on the side. Um, so the traffic rail system that was there until recently, that was damaged in a few of those flood events. And another key point is each of those segments weighed approximately, I think it was about 700 kilos from memory. Whatever the number was, it was far too heavy to be folded down by hand. This required lifting equipment or forklifts on the bridge to actually fold it down. Before we built the duplication, this was the highest bridge for this local area. So it was always left open as long as possible to give safe access to residents. So it was always a race against the clock to come and fold these barriers down. And you needed lifting equipment that was slow and heavy to actually fold down the length of the bridge. So Seqwater were again very keen to see a much lighter weight system when they actually replaced these. Just after discussing some of these, some of the constraints at the site, after the new bridge was built in 2023, Seqwater engaged us again to design the retrofitting for this bridge, a new balustrade system. I'll go back to that previous photo. We considered quite a few options of how to do this. One of them was just, can we accept what's there? The short answer was no. Like, as it is, it's just not suitable to use as a balustrade. Big gaps between the traffic rails. You can't use that as a balustrade system. A child could just crawl directly underneath those barriers, and various other issues as well. So we considered, can we use what's already there and attach additional elements to it to make it a suitable barrier? The weight was still quite a big issue of these systems, so anything we added to it was just going to make the weight of folding this down even more of an issue. So we went through those few options. We looked at, okay, well, let's replace it with a new folding balustrade system that's more of a breakaway system with a fuse bolt. We looked at that, but that was quickly dismissed because the bolt needs to be significantly stronger than the pedestrian loading on the balustrade to make sure there's no chance that breaks under normal use. But then it needs to break well and truly before the bridge deck or the balustrade post reaches capacity. And the reality from what I showed before with that really lightly reinforced deck, there's just not enough difference between those capacities. The fuse system couldn't work and couldn't guarantee it would break before the actual bridge deck gave way. So we couldn't progress with a breakaway fuse system. And then we also had a look at replacing it with a slighter weight but sort of typical steel balustrading approach we could, but went through a few iterations with that, and we still found it to be too heavy to be something that could safely just be folded down by hand. So at this stage of the options development, this is when we first contacted Wagner's, knowing that they had a lot of experience with lightweight structures and barrier systems and in this area. So we the first contact with them, described what the problem was, and they were confident that they'd be able to work with us to develop the system. Like any other project, the first thing we have to do is define the requirements. The snip on the bottom right there is just a really brief summary of where we started with Wagner's. Some minimum load capacities, the strength that the system has to be able to resist. Deflection limits. These are all just requirements straight from 5100, AS5100. So like any other balustrade on a bridge has to be designed to satisfy that. And really just the only extra requirement was the maximum weight that each panel could be to make so that it could easily be folded down by two people in the hinged arrangement. So we quickly got traction on this, working with Wagner's. Like, we had an idea of what we wanted, but leveraging their strengths, whether it was their experience with their products and all their in-house knowledge. They also had specialists that we could engage with. So we very quickly ran through a few different options, because the first part, it took a few iterations to actually meet these requirements within the weight limit still. But yeah, working with Wagner's in-house and their specialist expertise, went through a few iterations and came up with the finished product is largely what you see on your screen there now. So the snip on the left there is a rear view of the concept we came up with. So the hinged base plate actually supports two completely separate posts rather than one common post, just meaning that every single panel has its own post that can be folded down fully independently of the panel beside it. So straight away, that limits weight considerably. The image on the right there is just a snip of the front view, or the pedestrian's view of the arterial barrier there. So all the hinged components of the base plate are located and sort of hidden underneath that bottom rail. On the rear there, you can also see some location plates. So this system didn't have any spigots or like rail connectors between them. Every panel stays independent except for those two plates at the back there, which are bolted together to keep alignment. So after they're folded down for a flood, they're lifted back up and aligned, so there's no snagging points, and it also looks quite presentable. The back of that alignment bracket at the top there also has some holes where we attach the actual restraint. So when it's folded down, they're tied down together and can't be lifted up during the flood water. And so this design concept is largely what was actually fully designed and built. So a photo here has yours truly demonstrating just how light the FRP panels are. So even though I'm pretty sure the work method statement doesn't say to lift them one-handed by yourself, I didn't volunteer to do all 140 panels. This was just to get an appreciation for how light the finished product was. But you can also see here the individual panels. You can see how they fold completely independently of the panel beside it, just by using those twin posts. In the photo here, and it is by design that you can't actually see too much of that hinge post down the bottom. We tried as much as practical to better hide them underneath the railings. And I'll hand over to Sam from Pensar shortly, but the first photo he has in his presentation shows this hinging mechanism quite clearly. You can see on the top there is one of the FRP panels from Wagner's attached to the actual folding base plate. On the bottom there is one that hasn't had the panel attached yet. It has a simple hinge arrangement with a bolting attachment and a stub post that sits up a few hundred millimeters that's actually used as the interface between the sort of galvanized steel components and then the Wagner supplied FRP above. So I'll hand over to Sam now just to have a bit of a discussion about some of the construction considerations.
Yeah, thanks, Matt. And thanks, Georgia, for the introduction. Good morning, everyone. I'm Sam Strofield from Pensar, and I was in charge of delivering this project for Seqwater. I'm going to briefly touch on the installation process of the CFT system, balustrade system. So like Matt said, the photo you're looking at is one of the hinged base plates we installed to support the new balustrading system. I can tell you there was a fair bit of planning involved in getting these in, just because of the Heritage Act's requirements. We weren't allowed to drill into the existing concrete deck. So we had to work with the original hold-down bolts that were already in place. That meant accuracy was absolutely critical. Matt was closely involved in reviewing the shop drawings for these base plates, along with the 3D surveys, 3D scans, and conventional surveys to make sure that the holes in the base plates lined up perfectly with what was on site. We spent a lot of time planning and double checking everything, and it definitely paid off. Everything went really smoothly. One of the main challenges that we came across was the bridge itself. Being built in 1926, it wasn't level. However, the CFT balustrade system was designed to sit level. Because of that, the existing hold-down bolts weren't long enough for the base plates, for all 150 base plates to sit level. Yeah, we couldn't level them off each other, so that became an issue because the hold-down bolts weren't long enough. We came up with an idea of using couplers to sit underneath the base plate to get that additional length. However, that wasn't going to work because there was a few variables that would have pushed the balustrading system out of spec. With guidance from Pensar, Seqwater made the call to just to install all base plates 15 mil off the concrete substrate. And looking back at that was the right call. There is a slight waviness, but over the full length of the structure, it's barely noticeable to the average person. So once all 150 base plates are in position and set, we moved into installing the CFT balustrade system. We coordinated the delivery of the 140 pre-assembled panels in 2 separate loads, and we started from one end of the bridge, being the east bank end, which is the end you're looking at now. The process itself is pretty straightforward. We removed the bolt connecting the bottom rail to the vertical member, which was in that photo, first photo, Matt, when I started talking. You can see the bolt, that bottom bolt that's running through the stub into the bottom member, into the vertical member. Then we slid the CFT system over the stub and then reconnected that bolt back in place, and that was it. Again, thanks to the planning and drawing views and survey verification, and with Matt heavily involved throughout, every panel fit perfectly, and yeah, as intended. Once all the panels are in, we attached all the alignment brackets. We obviously grouted, placed locking pins, and essentially that was the installation process throughout the full length of the structure. Yeah, like I said, everything went perfectly. The planning from Wagner's, from GHD, and I'd like to say from us too, really did play off. So with that, Matt, I'll hand it back to you, mate, and you can continue on.
Yeah, cheers. Well, I was just going to steal one of your photos here just to show off our bridge downstream. So you can just see downstream here is a bridge that was completed 2 years earlier, which is where the traffic was switched, and this bridge now continues its life as a pedestrian bridge for the area. But you can also see with this finished product, the finished installation here, those brackets I was talking about at the rear of the system. You can see a bolt in the front hole of that bracket, keeping them aligned. But and like Sam mentioned, it's, you know, I'm sure you can measure and find a wave, but it looks like a beautiful straight system actually installed on site there. When they're folded down, again, Sam, I'm just stealing one of your last photos here. This is how they're restrained when the floodwaters actually come through. So those previous traffic barriers had about 12 metre long panels with a single, fairly similar system to this, just a tie essentially holding them down, tying to each other and stop them lifting during the flood. So that was for a fairly large 12 metre section that could be picked up or damaged. So to avoid having that same damage again, we've just aimed to have the most robust system that we could. Each of these individual panels, there's one tie down for each pair of panels. So they're actually quite, when they're folded down, there's a lot more restraint per area of balustrade. But also because they're broken into separate panels, if there did happen to be a damage or one of these ties wasn't installed correctly for any reason, if there is something lifted up and damage during this, it should be quite isolated for a repair, as opposed to one of those photos I shared earlier where it was like a zipper pulling off concrete the full length of the bridge. But yeah, I think that's everything I hope to share with this one, but I'll pass back to Georgia so we can go into the Q&A session.
Beautiful. Thanks so much, Matt and Sam. Thank you very much for your presentation. That was fascinating to travel through time with you guys to see where that bridge started back in 1884 and to now see that concept, the innovative FRP collapsible handrail concept that's in place now. So thank you very much. We're about to dive into the Q&A session, but just before we do, I wanted to tell you very quickly about Wagner's CFT design guide and a brilliant blog about the difference between manufacturing and fabrication. Wagner CFT design guide is a key resource for engineers working with our FRP profiles. It provides clear design methods, comprehensive section and connection data, and aligns with relevant Australian standards. Whether you're working on new builds or maintaining existing assets like the Mt Crosby Weir Bridge, it's a practical tool designed to support efficient and reliable design. So if you'd like to read or download the design guide, use the QR code on the screen now, and I will also include the link in today's follow-up email. When we talk about manufacturing versus fabrication in the context of FRP profiles, it's more than just industry jargon. The distinction really matters, especially to engineers. Manufacturing is where the product is made. It starts with raw materials where fibres and resins are selected, combined and shaped through processes like pultrusion to produce standardised FRP profiles. This is where material science, chemistry and quality control come together to lock in the fundamental strength, durability and performance of the product. By contrast, fabrication happens after manufacturing. It's the process of taking those manufactured FRP profiles and cutting, joining, and assembling them into structures such as bridges and boardwalks. Fabrication requires precision and engineering skill, but it does not change the inherent quality of the FRP material itself. The difference matters because you can't improve weak materials through fabrication alone. A structure built from poorly manufactured, imported FRP will never perform as expected, no matter how well it's fabricated. So when specifying or procuring FRP, engineers need to ask, were the profiles manufactured here to recognise standards or just fabricated locally from imported components? That clarity ensures performance, compliance, and long-term value. Use the QR code on the screen now to read the full blog on the difference between manufacturing and fabrication, and I will also include the link to the article in today's follow-up email. I'd now like to welcome Wagner CFT General Manager Ryan Leeson, who will be facilitating the Q&A session of the webinar today. Ryan, let's have a look at some of those questions.
Thank you, Georgia. We'll pile straight into one for Matt to start with. How did you factor in the debris mat into your design? Was there anything factored, or was the assumption worked that it would always be collapsed?
It definitely was always assumed to be collapsed. So I guess whether you call it a luxury or not, in this case, we'd seen what happened if the barrier was left up. This has never been designed to stand up and resist those flood forces. It's no matter what we do, unless we go through and replace this weir, it's going to have the same effect, the same result if it's not down and tied down. In terms of actually designing for the debris mat, we did do some numbers on in the folded down state, what sort of forces we're expecting in that tie down system. Now, all the calcs we did actually showed that it worked extremely easy. Like when it folded down state, the force that we could get on those straps to restrain it, it seemed like we could get away with something a lot smaller or space further between. But again, we can't ignore that in 2011, one tied down with a steel bar spotting 12-metre length that the calcs say shouldn't have been a problem. It may have been taken out by a log or something, but it has failed. So when it came to the restraint system, robustness was key. We did some calcs, but it was sized up from there from practical, just we're trying to avoid that same damage happening in the future. So it's a very roundabout way of saying it was governed by other things.
Right. Is the actual aluminium balustrade infill, is that sort of considered sacrificial? Is that how this design would work, that your main structure would stay in event of debris building up, that the balustrade, which is more easily replaced, would be sacrificial?
That was it was discussed at one stage. Do we, because if that balustrade paneling in between lets go and allows a lot of material through, it's still not the key design case. That's just maybe a little bit of redundancy if it was left up in a minor event, or if one section stood up, maybe that can go to relieve the stress. But reverting back to it's 100% designed to be folded down anytime this bridge goes underwater. Seqwater have their operations team coming out to fold it down. Everything else that may work in that favour is maybe just a bonus.
Yeah, understood. So question for you then, Sam, how long does it take for Seqwater to get out there and collapse this? And I guess the fact it's not road link will enable earlier in the process of preparing for floods?
I think it all depends on the resources, but if you saw that photo of Matt, he was able to do it by himself. But I
can't guarantee that would be very fast, though. So.
I think generally 2 men would get down there and get one side done within half an hour, and the other side again in another half an hour. So I would say an hour max. The panels, I think, from memory, weighed about 50 kilos. So But yeah, very, very lightweight. So 2 men could do that quite quickly, and get it down within the hour for sure.
Was there any, Sam or Matt, was there any example structures or anything similar to this that you're aware of that you sort of examined during your design phase of the project?
Well, during the design phase, there was nothing exactly like this, but we definitely took inspiration from a few others. So once we started talking to Wagner's, you guys had examples of quite a few balustrade systems as starting points that we could work from. I don't believe you guys have done any specific folding ones with your FRP product before. And the actual system with the twin posts, we'd seen used on another bridge with steel balustrade. So we hadn't seen this exact combination used before, but it has sort of taken inspiration from a few existing ones to come up with what we have today. Something, yeah, I can't emphasize how light it is. Like it's up, it's so robust, it's stiff. When you're folding it down, it's unbelievably light.
Okay, and Sam, for you then, from a construction sort of tolerance point of view, you obviously spoke around the scanning and sort of traditional survey that was done to get your tolerances and your positioning. Were the individual elements then fabricated by Wagner's, post the installation of the base plates when you knew exact dimensions, or how did that sort of process flow out to make it fit when it turned up?
So I think we were supplied a survey from Seqwater and GHD. Obviously, we did our own due diligence. We got in a 3D scanner, and he took measurements of each individual bolt, which then we passed on to our fabricators for the base plates, and then you guys as well. We put together Wagner's puts together some shop drawings, and then obviously Matt was heavily involved in reviewing those drawings. But yeah, we got the 3D scan done straight away prior to any fabrication.
And I guess there's a bit of a potential overlap there. It's quite often in construction jobs that, particularly in our space, the biggest tolerance issue that we run into is piling, and the juggle is always: do you wait to fabricate superstructure until piling is complete, then you can custom fabricate superstructure, or do you build tolerance and have green stick on all of your members to enable it to be on-site fabricated? Was there any sort of learnings you could take from that if you were to tackle a project that you either could or couldn't factor that in? Was it save on site construction's time and sort of?
I think we were. I think we're pretty lucky because there was more scope involved than just the bridge. We had some civil works as well. So the contract was broken up into 2 separate portions. First separate portion was the civil works on West Bank and East Bank. So during this time, I was able to focus on the actual the design and the review of the CFT system and the base plate. So I think just how the job was programmed and the contract, we had that time to really focus on the design and make sure everything worked and fit on site. So with that, yeah, we just had the resources and the timing given the program and the contract. So that was, I guess, a blessing on our end to get everything bang on. Yeah,
I guess that makes sense. It often comes down to construction sequencing to determine what the most appropriate construction method was. There's a question online here. Was there any consideration, maybe for you, Matt, any consideration given to an automatic collapsing system rather than having to do it manually?
Well, we did this. I think I mentioned at the start. We discussed like a breakaway sort of fuse system, which just wasn't realistic for the strength of the deck on the edge. There was too much risk that the deck would break before the fuse bolt would break. I guess the next step up from that, I'm not sure if the question was aimed at an electronic or some kind of mechanical system that would fold it down fully automatically. Sounds fantastic, but it also sounds like the actual answer is we didn't consider going to that level of detail. It seemed quite complex and overkill for replacing a few hours of labour. But yeah, the fuse, the trickiest we tried to get with that was a fuse system that could break away and fold under floodwater, but it just wasn't feasible with how weak the deck edge was. I'd love to see someone go ahead and do something similar with a big mechanical system. I don't want to be involved in having to design the mechanics of that, but I'd love to see it in action.
That's where we get our mechanical friends involved. All us civil engineers can sit on the sideline, I guess. There's another question here. I'll just find it on my screen here. Is there anything stopping SEC water from dropping more than one panel at a time, reducing the number of dismantled bolts that need to be taken out?
I don't think there's anything stopping them doing that, but I think good practice is to follow the methodology that we provided SEC water, and that was the one panel at a time. There are some locking pins that you need to take out, so that is the fiddly part of the collapsing the system. But I would say you could probably do it in 2 panels, and given the amount of people you've got, I think it would just be a trial and error situation. But yeah, it's definitely recommended to do the 1 panel at a time.
Yeah, and I think the only thing I'd add to that is there is on the western end of the bridge where it was extended after the flood, it has quite like it's a 120 metre long straight bridge, and then it has a huge curve and vertical curve and slope on the edge. That curved section would have to be broken into individual panels to fold down.
Yeah.
If this was a dead straight bridge, we may have considered going wider, but I think the brief being trying to minimise the amount of weight, we got it down to that lightest one. In the straight sections, there's nothing technically stopping them folding it down, but like you said, it's following that safe procedure they've agreed on. You don't be changing it when the floodwaters are rising up the bridge near.
Understood. And with that method, Matt, Dan, what does happen with the bolts? Do you put them back in there, or do you just take them off site?
Yeah, so it's literally just I think it was from memory, an M16 threaded bolt that you just slide through and a nut on the other end. So it's literally pulling it out, dropping the balustrade system, and then just putting the bolt nut back in place.
Yeah, understood. Okay, well, maybe I'll pass to Matt and then Sam, just to give you the opportunity. Is there anything else that's sort of come up in your mind during the session that you think we haven't asked that is interesting to the group?
I don't know. I can show more photos of the old bridge. I think you already touched on it, Sam, but there was when you guys got involved and we were going through surveys, there was quite a bit of time we went backwards and forwards with surveys, arguing over millimetres here or there, which at the time probably felt like I was being a bit too fiddly for you. But I hope you agree that the end result where we weren't having to hack holes out of base plates and things on site was, if something similar to be done, I'd spend all that time in that planning again before trying to get these things fitted on site.
100%, totally agree. I think the planning was 100% worthwhile. So, and because obviously everything went in so smoothly. So yes, agreed with Matt there. The number of reviews and back and forth was definitely worth it.
Fantastic. Well, I'll leave it there, Georgia, and pass back to you to wrap up the webinar. Thank you, Matt and Sam, for your time.
Thank you.
That concludes our presentation today. A big thank you to Matt and Sam for your involvement, and thank you to Ryan for facilitating the Q&A session. If you'd like to share your thoughts on today's webinar, please feel free to complete the feedback form by using the QR code on the screen now, or I will also just pop that URL in the chat facility as well. Or perhaps you'd like to be a guest speaker. If that's the case, fill out the feedback form and let me know, or you could always reach out to me on LinkedIn, send me an email, give me a call. However you want to contact me, I would love to hear from you. Coming up in March, we'll be discovering the differences between pultrusion, pull winding and filament winding, and how each method impacts fibre reinforced polymer performance and applications. With guest speakers, Wagner CFT lead R&D technician David Bolin and production engineer Alfred Ajak. So if you're interested in this webinar, use the QR code on the screen now to register for your free online seat or to receive a recorded copy of the webinar. The link is also in the chat now. That concludes our webinar for today. Thank you very much for coming. We're going to go out on that video of the Mt Crosby collapsible FRP handrail system from the beginning of the webinar. Enjoy, and we look forward to seeing you next time.